Alrighty, in today's lesson, we're doing compound interest. Our success criteria for today is that we can write an exponential equation to model it, and that we can also apply exponential functions to calculate account balances. So we're going to go ahead and skip the recall for today. So I'm just going to write skip on that. And then we are going to take a look about what we're learning. So we do a lot of exponential growth in real life situations when it comes to financial accounts. When money is an account, it earns interest, and it can be calculated different ways. So the first way is simple interest, and in simple interest, it increases linearly, that you get the same amount each time. And then we have compound interest, which is what we're going to be focusing on more today, which is it increases exponentially. You will receive the interest formula for on the test. Okay. So some key things that you need to be aware of, which will not be given into you on the test, is that I represents the interest after year T. P is the principal amount or the initial amount or the primary, what you start with. R is the interest rate. And this is super important here. It's always as a decimal, so you're going to get it as a percent, and you're going to have to convert it to a decimal. And then A is the amount that's accumulated over time, and N is the number of times per year that they're going to reassess and give you interest on top of interest. So there's a couple of things that I need you to know. If N is N equals 1 when it's annually, because that happens once per year. N equals 4 if it's quarterly. Oh, I forgot this one. N equals 2 if it's semi-annually. All those semi-annual sales happen twice a year. N equals 12 if it's monthly. N equals 52 if it's weekly. You get the idea here. So that's how many times that they're actually going to compound the interest, and so you can start earning interest on interest. So the first example says Karen has $24,000 to put into a bank account. Bank A offers simple interest, so it's going to grow linearly, so we would use that one. And Bank B is compounded quarterly. Write an equation to model these banks. So Bank A. So before we do that, I just want to show you guys right here. So we have to write an equation. So the variables in Bank A, which are the simple interest, are I from right here, P, R, T. So I just like to make a chart for that. So we know that the primary amount that she received or that she has to put into this account is going to be $24,000. And Bank A offers 1.8%. So 1.8% is a percentage. So if you want to convert it to a decimal ends with an L, you're going to move that decimal point 2 points to the left and fill those holes in with zeros. Okay, I think I did that silly. Sorry. So it's going to go 1, 2. Yeah, there we go. That's better. Okay. So we're writing the equation, so we're going to leave this as I, and then this is $24,000, and then this is 0.018, and we don't know how long she's going to leave it in there, so we're going to leave this as T, and then we're just going to plug all that into that formula. So 24,000 times R, which is 0.018, times T, like that. Okay, that's it for that one. Use the other equation to model Bank B because it's compounded quarterly. So let's take a look at that again. Compounded quarterly right here, and at 1.5%. So in order to do that, I'm going to look at all the variables in my new formula. So it starts with A, then P, then we have a 1, that's a number, not a variable. Then we have R, N, and T, and we do have N twice, but that's okay. So we're trying to write an equation, so that's going to be A, and we're going to leave T as T, and then P for this, the same amount that she starts with is $24,000. This rate is 1.5%, so we need to be very careful. We're going to move that decimal place over once, twice, so that's going to be 0.015. And then because it's compounded quarterly, quarterly is 4 times a year, so then I plug that in. So now we're going to just plug into our equation. 25,000, 1 plus 0.015 over N, so N is 4, and then 4 times T up there. And that's it. So moving on to part C, it says if Karen plans to leave the money in an account for 10 years, which bank should she use to save her money? Well, we're going to assume that she wants to get the most money out of this. Now we have to keep in mind here that Bank A is an interest formula, not an account balance. So we're going to have to add it to her original. So I'm just going to separate this real quick. Here's Bank A. I'm going to take her interest formula and times it, put in T equals 10 because it says right here 10 years. And then I'm going to plug that into my calculator just as is. And that means that the interest that she's earned is $4,320. That doesn't make sense for her money to go down if it's supposed to be growing. So what she did is she started with $24,000 and then she earned $4,320. So in total, after 10 years, she has $28,320 in the account. Now we're going to go to Bank B, and in Bank B, it's the same thing. T is going to equal 10, and we're going to see if the compound interest makes more money than the simple interest. Generally speaking, compound interest is going to make more money the longer that you are having it in the account. So here's our formula right here. Just make sure you plug it into your calculator properly. So it's going to be 24,000 times 1 plus, what is that? 0.015 over 4 for that quarterly. And then we're going to raise that to 4 times 10. And there we go. It's money. So we need to make sure with the money that we round to 2 decimal places. Euro, you only round once. The number next to it is 0.200. So that third zero is not going to round that previous zero up. So we're going to leave it as 0.20 as her change. So her account balance is $27,876.20. So if she's only leaving it in there for 10 years, then it makes more sense because this has a higher interest rate. It makes more sense for her to use Bank A. So our answer to this question is that therefore she should use Bank A because she makes more money. Now, if she's going to pull it all out and use it after 10 years, then maybe that's fine. But what if she's like, nah, I'm going to keep saving it? Which one will do better even longer? Because over time, exponential is going to grow quicker than the simple interest one. So let's see for this one. It says, what if she's going to leave it in there for 30 years? So that means that T is going to equal 30. So I'm just going to plug that into each formula again. And then that gives me that we have interest of, wow, that's nice. After 30 years, she didn't do anything with it, but she made almost half of what she put in there. So it's going to be that 24,000 plus the 12,960. So she makes $36,960. Let's see what she's going to get when she takes it to Bank B. So the account balance, not the interest, but the actual account balance is going to be up here. We're going to change that T to a 30. So if I go back into the calculator, hopefully I enter, and then I'm just going to do, oh, I don't know why I did that. I was doing the right thing. Okay. And she makes 37,607. And here's where we have to really look at that, because we're 82 cents, but the 6 right there is going to make that 2 become a 3. So on our total here for A, it's going to be $37,607.83. So which account makes more money? The account that makes more money is this one. So we are going to say that this time she should use Bank B. Okay, let's go ahead and take a look at the back side where we switch to a different form of interest. Actually, we got one more with this, so let's see what we have here. Always like to highlight all my information. This is that fuss. What are the facts? So we're kind of shortening it, even though I probably shouldn't. Trevor deposits $40,000 into an account that pays 2.9% annual interest. Find the balance after 5 years if it's a compounded and not a simple interest. So we are going to see quarterly and then daily. And you can see the vocab that I already gave you is on the left-hand side right there. So for this one, we are just going to use our formula. So A, P, R, and T. A is what we're looking for. Trevor starts with $40,000. 2.92, move it once, and then move it twice. So that's 0.0292. Because this is quarterly, that means n equals 4. And then it says for 5 years in the problem. So then we're just going to plug it in. And then you're going to plug it into your calculator. And then you're going to get that this equals $46,263.31. And then if he does it daily, these charts are just a way for us to organize our information and just give us a second to make sure that we have plugged all of our numbers into the right variable. Daily is going to be 365 for N, and it's still 5 years. So we're going to set this up. Really, the only difference is, held that too long, that this is 365, and that's 5 times 365. So when we do all that math, we get that it's going to be at $46,287.58. So it's not really that much of a difference, but compounding it daily means that you're earning interest on your interest, so you will earn more money the more times that you compound it, as long as everything else is the same. Okay, the next formula we're going to learn is the continuously compounded interest. So this one is if every time you put something in to your bank account, it would just continuously be compounding. It wouldn't be done annually. It wouldn't be done quarterly. It would be done annually, continuously, which for this, they say is equivalent to once per second. So we could use the other formula and use a seconds instead of like daily or annually, the number of seconds in a year, but that would be a little bit too much to do. So it says, what would Trevor's account balance from example B be after 5 years? And again, this is our formula right here. So we need all the same information, but we have E, which is the natural number. So we're going to have that in our calculator. So here is my A, P. This E right here is like pi. It's an actual number, so it's not a variable. And then R and T. So we're trying to find A. And we know that the initial amount from the previous problem was 40,000. And then R is going to be 0.0292, same as from the previous problem. And then time is 5 years. So this is just using, we call it the PERT formula, P-E-R-T, PERT. You plug in all your quantities for the variables. And then we're going to plug it into our calculator. So I'm going to show you this on this calculator right here. You're going to type in 40,000. And then if you notice where it says ln, it's next to the number 4. In blue, you can see an e to the x. So you're going to type the second button and then the ln button. And then we're going to put in 0.0292 times the 5. My kiddos are clearly having fun in their bath time. So there's our answer right there. And then we're going to go back into our notes and write that it would be $46,287, and checking for rounding, it would be 85 cents. Okay, so that is that one, and we're going to skip the apply for today. Alrighty, that's it.